Bismillahirrahmanirrahim. In our last class, we had seen the SN diagram and how it was of two types depending upon the material. In one kind of material, most notably steels, you have this knee here, and after this, the curve becomes a straight line. And this means that if the stress amplitude of a completely reversed stress is equal to the so-called endurance limit or less than that, then there should be an infinite life. Now, nobody has tested anything to infinity, but when we talk about infinity, we're talking about, let's say, 100 million cycles or 1000 million cycles. For our purposes, that's infinity. Now there's another kind of materials in which there is no such need. So the fatigue strength of the material is a function of the applied stress amplitude, and there is no stress level at which you can say that the component will have infinite life. So in such cases, if you look up your the appendices at the back of your book in table A24, you'll see that the fatigue strengths, also called SF, of such materials is always given at about 5 into 10 raised to the power 8 cycles. So the strength is corresponding to these many cycles. For materials of this type, you'll always find in data the fatigue strength will be given as endurance limit. Now, there's a usual question why a knee is present in one case and no knee here. So the material scientists, they offer some explanations. For example, they say that the materials which are capable of strain aging, as steels are, they display this, they demonstrate this knee. And the materials which are not capable of strain, these are capable, and these materials are incapable of strain aging. Now, what is strain aging? Strain aging is the ability of if you can look at it like this. Because of fatigue, the strength of the material is basically decreasing with every cycle. So because of fatigue, the strength goes down, but there is a competing mechanism, and that is strain aging, in which the flow stress of the material keeps on increasing with every cycle. It is as if in every cycle the yield strength of the material keeps increasing slightly, but it keeps increasing. Now, at higher stress levels here, it doesn't matter because this phenomena always wins over this one. But there comes a situation, a stress level, a stress amplitude level at which this starts competing, and they two are in equilibrium. And at that time, at that stress level or below it, you see that because that's an equilibrium, the fatigue is not able to decrease the strength of the material any further because of a competing mechanism here. So stress levels below this, you can experience infinite life, the so-called infinite life. Now, why strain aging occurs? Well, again, we have to go one step back, and the material scientists tell us that there are some impurities or interstitial atoms like carbon, nitrogen, that hinder the movement of dislocations, and because of dislocations, the flow of atoms along slip planes, they are very important for in the crack propagation. So if that stops, then obviously there'll be a phenomenon called strain aging, and that is ultimately which what causes this need to be here, and the life after this to be in a life below this stress to be infinite. Now many materials are not capable of such a thing, and so there is no infinite life, so we always design them for a certain number of cycles. Now obviously one can go back and back and find more detailed explanations, but for our purposes this is about what we need to know. Now it will be a mistake that just because we have this point after which there is infinite life, so we can, if we design something in this region of stress, then it should be infinite. So just because we know that this is the case, we always design everything for infinite life. So this is a mistake. We don't design everything necessarily for infinite life. There are things which we design for infinite life, but there are many things which we don't. And the reason being because brittle failure is just one of the modes of failure. There are many other modes. For example, things become obsolete, things wear out, etc. There are so many things. You may not even want to design something for infinite life because you know that the technology will become obsolete before that. So it's just a wastage of time and money. So there are cases where you will be, obviously there are many cases where you will try to put your stress levels here or below this so that there is infinite life. But there will be many cases where you know that, for example, I need my component to work till 10 raised to power 4 revolutions. That's all I need, or this many revolutions. For that, this is the stress level that I need to subject my system to. And obviously if the number of cycles required are low, then I can put a higher amplitude of stress. That's very obvious. Now this is the first thing to know about this region, because if you recall from this is the finite life region, and this is the infinite life region. And this, of course, the low cycle fatigue, which we won't be going into much detail. Now if we just discuss this all important SN diagram or SN curve a little more, there are some things to note here which are very important for the rest of the development. There are a few things, and here I'll be confining myself to steel. This is the most predominant widely occurring material in engineering design, and we'll be focusing on this a lot more than other materials. So the first thing to note is that here this is equal to the ultimate tensile stress, stress or ultimate tensile strength of the material. And that it's very obvious. How many cycles are there? There's 0 cycle here, or you can say 1 cycle. If you load something to its ultimate tensile strength, how many cycles do you need for it to break? Actually it is less than 1 cycle. It's maybe quarter of a cycle, because you don't need to come back. It just breaks in maybe quarter of a cycle. So but we put it at 1. Now experiments also give us the value of SE here, and this SE, the endurance limit, is also called SE prime. I'll just go into detail about this later on, but for now, SE prime is the endurance limit for the test specimen. You know that the test has a number of specifications, ASTM standards. It has to be polished. It has a certain dimension, a certain kind of completely reverse loading, and so on. There is a lot of detail. But in real life, your components, even of the same material, will not be conforming to all those requirements that you can see, and you can make sure that they are applied in the laboratory. You cannot ensure, and obviously the sizes, the shapes, they'll be different depending upon the functionality of the part. So in real life, you will be talking about endurance limit for the real components. So there's a difference here, and I'll cover this later on. For now, we are talking about the test, so maybe we'll be focusing on this one here. But the same story goes for the SE also. Now, this is the end of the low cycle fatigue, and here the strength comes out to be a fraction of a fraction multiplied by this SUT, and we can find this out very easily because a lot of data, we have a lot of data at our disposal. A number of tests have been carried out upon many materials, and we'll discuss this later on. This obviously is the endurance limit. Now, it's important to know that this line, one would be forgiven to think that there were points like these and there were so many specimens that were broken and not broken in this case, and you just drew a line through them. But that would be a mistake, because for any level of stress, for example, if you apply your specimen to this level of stress, obviously in our last class, please recall that we said that fatigue is a statistical enterprise. Every material has different kinds of flaws, different number of flaws, different orientation of flaws, and there's variation everywhere. So if you apply the same material to this amplitude of reverse loading, it won't just break here. If you take 100 samples, maybe you'll get this kind of a result. Some will break here, each one will last for a different number of cycles, and then it will break. The same story goes for every stress level. So the line that you see here, a very neat line, it is just an average of all these lines, of all these points. And in this case also, there will be a variation. Only here, some of the samples, this is a breaking, these are breakages. Here it means that it just does not break, it keeps on going. And the interesting thing is, some below this line will also be like this. Some will break here obviously, and some above this line will also break. So this kind of situation is there. So this line, it is very important to know, it only represents a reliability of 50%, because we have just drawn this at an average of all those points. If you want to, for example, raise our reliability to 90%, maybe we'll have to pass another line, the so-called lower bound. Maybe then this is a reliability of 90%, and we can increase the reliability. But The important thing to know is there is a distribution here, and even if you go to standard deviations, even then there will be maybe 99 point something percent of the points will be inside, but still some points will be outside, and that is the nature of any statistical process, any statistical phenomenon. So you can never cover all the points, but for now, in our test, the reliability of 50% is the standard one. The figures that are reported are based on this, and we'll see when we need a more reliable estimate what we do. We'll see that later on. Now, what if we have a new material? You have a new material that you want to use for some application where there is fatigue. Now, what should we do? Obviously, one way is to perform an experiment. And if the material is old and the results are published by someone who has experimented, and then you can take that value. But again, that value will be, those values will be SE prime, and the data will be obviously experimental data from the lab. So what you do in real life, that's a separate question. We'll come to that later on. But what if you have a new material, you don't find anything reported in literature? Obviously, the first thing that comes to mind is, let's have a test for it. But like I just discussed, there are so many points here. For one point here maybe represents 100 samples, and you take the average. So it's an expensive thing. Testing is expensive. It's not just breaking one specimen and then reporting the results, because that may be a extraordinarily strong sample or a very weak sample, depending upon the micro cracks or the imperfections in the material. But fortunately, there is a wealth of material. Many different materials have been checked, have been tested according to the ASTM standard, and there are some well established trends. We have compared the test results of different materials. The test results meaning the rotating beam specimen, the rotating beam test, and then we have compared those results with for example, the tensile test of the same material, and we have some very good approximations. We know that for a certain tensile strength, what is the uh, endurance limit, or for example, what is this fraction f that you have to multiply the SUT with to get the residual strength at this 10 raised to power 3, which is the end point of the low cycle fatigue. So two such trends are very important, and we'll be using them a lot. One, obviously, again, I'll just summarize again. If you have a material whose tests are available, you have this diagram for a particular material, then you can just read these values, this F and this SE from the graph itself. I'm talking about a material for which you don't have data readily available. So because there are certain trends, the first one, and it can be found in your textbook, this is figure 618. It basically gives you the relationship between the ultimate tensile strength and this fraction, by which after 1000 cycles this strength has been reduced, and it is something like this point is 0.9, and this point is the lowest point is something about 0.78. So this much strength has been reduced by the time 1000 revolutions have been completed. And because SUT is increasing, so you can say that for higher For stronger materials, they lose their strength faster. So you just read the F from here and you can use that. The second important thing that again is based on some well-established trends done on many materials over a long period of time is the relationship between SUT. Again, SUT, this comes from the tensile test. There's no difficulty about this one. So how to relate this again, SUT with the SE. Again, I will write prime here because this prime means we are still in the domain of experiments. We are not talking about the endurance limit of a real world part, for example, a plate, for example, a shaft, because here we are just discussing rotating beam experiment specimens. And in the real world, you may have different kinds of loadings. Maybe the surface is not polished, and so on. There are so many other things. So we are still in the domain of experiments. So again, I'm putting a prime here. And what will we do when we come to this? That is something we'll see later on. Now, there's another trend between these two, and it's a very interesting trend that up to a certain level, it's a linear function, and after that, it just levels off. And although there is a slight variation, obviously, as the tensile strength increase, the variation starts increasing. But after this, it levels off. So again, we are talking about this sort of a thing. It's not just a line, but something like this. So we can sum this all up with reasonable degree of precision. Although it won't be very precise, but for us, for the maybe for preliminary design, that should be enough for us. And we must bear in mind that these things are used for preliminary design. If you are going to design a very critical component, for example, for an aircraft, ultimately you will have to rely on some sort of testing. So this is not a replacement of testing, but for preliminary design, obviously, you just want to see the ballpark figures, and maybe the process gets refined later on, and then you design something very accurately later on based on the experiments. But for start, this information should be enough. So SE prime is simply half of the SUT, provided that the SUT is less than or equal to 1400 MPa. This is 1400 MPa. After that, levels off. So SE dash is equal to 700 MPa for this. Obviously, it means that this is 700 MPa. And this you can find in your figure 617. This figure. But if you have this equation, you don't need to rely on this figure, because we don't have equation for this. For the values of f, you have to rely on this figure in this figure 6.18. So with this information, the designing in this part below the endurance limit, that is easy. Designing before 10 raised to power 3 cycles, that is low cycle fatigue, we won't be discussing that too much. What we are left with is this so-called finite life region. How do we design for a certain number of cycles? How do we know what stress amplitude will be required for that many cycles? Or conversely, if we know what the amplitude we are going to apply to the body or to this object, then how many cycles will it last under fatigue? So how to know that? Let's see. So we're talking again, we are talking about this region 10 raised to power 3, and we are talking about steel here. This is log S. Here we plot strengths or stresses, but both in the log, and here we have log of number of cycles. So how to design something in this region? Now SF, we call it fatigue strength. It's basically, if you recall, we have plotted this on a log scale, but actually if you don't use a log scale, it's a curve. So let's approximate this curve by this. Now when we linearize it by using log, obviously we can write it as here this is an equation of a line, because this is a line, and this is y, this is c, or the y-intercept, and this b is m, slope, and this is our x. So how can we find the values of a and b? We know the two boundaries, the boundary conditions here and here. Stress cycles. For 10 raised to power 3 cycles, we know the stress to be FSUT. And for 10 raised to power 6 cycles, the stress is SE, or again SE or SE prime. We are focusing on SE prime here at the moment. So if you put these values for n and this value for stress here, and you'll end up with two equations, obviously, one with this, one the other with this, and if you solve them simultaneously, the result which you can verify for yourself, again please bear with me, this SE or SE, because it is valid for both. At the moment we are only dealing with the experimental samples, but soon we are going to use real world components also. These are the values of A and B. So once you know for a certain, obviously this A and B will be different for different materials. So these are material properties. These depend upon materials. And once you know A and B, then if you want to find how much the fatigue strength is for a certain number of cycles for that material, you just plug in the values of A and B and you get this. This will tell you that for a certain n, this is the value, and we should write it like this because we're still in the experimental domain as yet. This much load, you cannot go beyond this load for the number of cycles to be. If you go beyond this, then the number of cycles will decrease, obviously. So this is your one of the solutions. Now conversely, sometimes you know that you are going to apply this much stress amplitude, completely reversed amplitude, and you want to find out for this stress what will be the number of cycles that the component will sustain. And let me remind you here that again, this is, we are talking about 50% reliability here. This line is at the mean of all the points. Now for this case, if you just rewrite it in terms of n, then n will come out to be, let's call, this is called strength. We are not talking about strength now, we are talking about stress now. So completely reverse stress over A, this goes in the denominator, and this B, this is the equation that will give you the number of cycles if you know how many, what is the amplitude of completely reverse stress that you're going to apply on that system. So this equation works both ways. and we are going to demonstrate it soon using an example. Now, to sum up, there are three regions in the SN diagram, and we are talking about steel here again. One is N is less than 1000. We are talking about this one. This is low cycle fatigue region, and it is dealt with by strain life method. We won't be discussing this low cycle fatigue in our course. The next is the region where the number of cycles are greater than 1000 and less than 10 raised power 6, 1 million. Here the equation that we'll be using is this or this. Again, the difference between two is this one is for real world applications, this one is for experimental specimens only. This is called finite life region, and n greater than 10 raised to 6, of course you just make sure that your stress is less than the endurance limit or less than this prime, and this is infinite life. This is your this is the summary how we'll be dealing with these two. And let us do a numerical problem here to reinforce what we have learned today. So the problem states that we need to estimate for 1050 HR. This HR stands for hot rolled. We need to find out the rotating beam endurance limit at 10 raised to 6 cycles. Endurance limit is for 10 raised to 6 cycles. The fatigue strength of a polished rotating beam specimen corresponding to 10 raised to 4 cycles. We are obviously talking about a rotating beam specimen. We are not talking about some real world problem. We are talking about polished and rotating beam specimen. So we'll be dealing with SE prime and SF prime. Number C, part C, the expected life of polished rotating beam specimen. We are still talking about prime values. Completely reverse stress, under a completely reverse stress of 385 MPa. So essentially, we are basically required to use these two equations. In one case, first of all, we need to find the endurance limit. That is very easy to find out. We'll do that. After that, second part, for 10 raised to 4 cycles, what will be the fatigue strength? What amount of completely reverse stresses we can apply for our specimen to last up to n revolutions? And part C is opposite of that, the expected life of polished rotating beam specimen. The stress is given now, so here we'll use this one. For a completely reverse stress of 385 MPa, how many cycles should we expect this to last? Now obviously we have talked about reliability. Our answers will be estimates because we don't know what kind of a specimen we get if we actually do the testing. It may be a weaker specimen with a lot of internal flaws and external flaws, or it may be a very good sample which is above the average. And remember that we are talking about 50% reliability anyway. All this data comes from 50% reliability line. So, but it will give us a ballpark figure. Now let's start this problem. Part A is very simple. We need to find out SE prime, and SE prime, if you recall, for stresses less than 1400 MPa, SUT less than 1400 MPa. Please recall this. We're talking about this. SE prime is simply 0.5 multiplied by SUT, and in this case, what is the SUT? If you go to the back of your book, and you can find out that in table A20, appendix A20, you'll see that for 1050 HR steel, the SUT is equal to 620 MPa. Now 620 is way less than this, so we are justified in. If it was more than 1400 MPa, then we would have taken 700, but in this case we are justified in using this. So 0.5 into 620, this is 310 MPa. So this is our part 1, as simple as that. Now for part B, obviously we need to use these two equations. But for these equations, we need to know A and B. So let's calculate A and B using the formula we just derived. A F SUT square over SE prime, again prime because we are in the experimental specimen domain. Now we need an F for this. What is F? SUT we know already, 620. What is F? F, we just discussed that it can be read from figure 618 against an SUT of 620 MPa. Here you'll find the value of F, which turns out to be 0.86. It's approximately equal because you read it off a graph, you cannot be very accurate. That's all right. So now we are in a position to calculate C prime, just 310, and this is 917.1 MPa. As for B is minus 1 over 3 log of FSUT. Now we know all these values already. Again we write SE prime here, minus 1 over 3 log of 0.86 into 620 over 310, and this is minus 0.0785. Now the fatigue strength is simply A and B, and we are talking about 10 raised to the power 4 cycles, and B is minus 0.0785, and for A you will 917.1, and this comes out to be 445 MPa. Kindly confirm these values. You should verify these. We have just done this. So this is the answer for part B. Now we come to part C. In part C, it is the reverse. We know the stress that we need to apply on the body, and we need to find out the number of cycles. So we'll be using the formula N is equal to, and this is the completely reverse stress. Just put in the values, 385 over 917.1, 1 over minus 0.0785, and if you calculate this, it is 63385 revolutions. This is the answer for part C, and that finishes this example for us. And now finally it's time to consider one more thing, maybe two more things. So to discuss the first thing first, if you know the Brinell hardness number, HB for a steel, then you can find out SUT, the ultimate tensile strength, is about 3.4 HB in MPa. This is for steels. We are talking about steels here, so. And generally, for ductile material, again it's a loose term, but for ductile materials, the yield strength is roughly equal to 0.75 of the SUT. Actually, it's 0.7 to 0.9. The factor is 0.7 to 0.9, but to be on the safer side, we can use this one without much error. Now, see what we can know about a material. If it's steel, what we can know from just one property. If you know the HB, the Brinell hardness number, all you need to do is multiply it by 3.4 and you get the ultimate tensile strength. If you know the ultimate tensile strength, we have already seen, you multiply it by SU, you multiply this by HB, 0.5 to SUT, and you get the SE prime. And in other cases, obviously for very high, more than 1400, you know it's 700. But and additionally, if you know the SUT, you multiply 0.75 with SUT and you get the yield strength. So from one hardness number, you know so much about a material. Obviously, there is a range, and there will be some error. It's not very accurate, but it's reasonably accurate. Now, I mentioned this because in some of your questions at the back of the book, the question only gives you Brinell hardness number and then wants you to do some calculation. So this will come in handy. Now, before we end, let me talk about SE versus SE prime. Obviously, we'll be dealing with these things in detail in the next class. But what is the difference between SE and SE prime? Because obviously, it's no use, it's not much use if you only can deal with SE prime, because it's just for experimental domain. In the real world, you need SE. So here let's write SE and here SE prime. This is for real world problems, and this is from the lab test or from some relationship based on that. Just like if you know SUT, you can calculate SE prime, but that is based on, again, so many different materials tested in the lab and you know the relationship. So we are still in the prime domain. Now, what's the difference? Obviously, if you're talking about this one, then it's conforms to ASTM standard. Conforms to ASTM standard. Also polished. Now, when we talk about standard, it must be polished, and exact dimensions mentioned in the standard. You cannot just take any sample size, because again the flaws will be proportional to the size of the sample and so on. And then fully reversed bending. It's not just any kind of loading. And obviously certain reliability level, 50% is normally reported. So there are so many correct procedure. There's a procedure. Now, there are so many things here. In real world problems, there will be a variety of shapes, obviously depending on the functionality. Surface finishes. You don't always get a polished surface in real life. There'll be different loading types. Some will be axial, some will be torsional, some will be a combination. Different temperatures, all sorts of variations. So we have seen what happens in a lab. We can speculate about which region we are talking about, infinite life or finite life, and how much number of cycles for a certain stress level, or how much stress level for a certain number of cycles. We know this, but that's still in the laboratory domain, the experimental. Uh, but what about real life, in real design? So we'll take this up in our next class, and we'll go into detail about that. Thank you very much.